Gibbs free energy is important in the matter of chemistry because it indicates whether a certain reaction will go through on its own, in which case delta G is negative, or vice versa. There are three different equations in which Gibbs can be expressed, each highlighting a different perspective. The first one indicates bonding and disorder. There are three different variables. Delta H is enthalpy, which indicates whether you are creating or breaking bonds. So if it's a positive value, you are creating bonds and using up energy from the environment to do so. And if it's negative, you're breaking bonds and you're releasing energy in the environment. Temperature is always assumed to be positive, and entropy is a matter of disorder, where if the value is positive, your product is more disordered, and if it's negative, your product is less disordered. So common problems you'll see with this type of Gibbs equation is whenever you're given a positive or negative value for delta H and delta S, and you're responsible on determining the sign on delta G. So if delta H is negative and delta S is positive, whatever is in this red box is going to be positive, and so a negative minus a positive value will give you an even higher negative value. And so for that reason, this equation will always be spontaneous because you're always going to get a higher negative delta G value. If delta H is positive and delta S is negative, then this red box is going to be negative, and so a positive minus a negative value, that will always give you a higher positive value by the end. So for that reason, this scenario will always never be spontaneous. And if delta H is positive and delta S is positive, then this value is always going to be positive, and so delta H minus a positive value, well, that's only going to be negative when whatever value that's in this red box is higher than whatever's over here. So in other words, this is spontaneous only whenever the temperature is high enough so that it can counteract the delta H value. And vice versa, if delta H is negative and delta S is negative, well, it's a negative minus a negative value. And so we need to make sure whatever value is in here is kept low so that we can preserve this negative value. So this is only going to be spontaneous when our temperature is low enough so that it doesn't counteract and make this whole value positive. So a common example of this delta G equation is whenever two hydrophobic residues, for example, when two blobs of water are coming together in water, unite. So when these hydrophobic residues are coming together, you might think delta S, which is a matter of disorder, is going to be negative, right? Because two things combining into one creates more order. Well, not exactly. One thing to factor in with this scenario is that these hydrophobic areas in water are surrounded by water molecules on all sides, okay? And this is known as a water cage or a solvation shell. So before these hydrophobic residues are coming together, you need to expel this water, okay? And it turns out it is a lot of water. So much so that the disorder caused by all of these water molecules fleeing over here and over here is way more than the order that's created when these two guys come together. And then whenever we're talking about delta H, right, that's bond forming and bond breaking. So when these water molecules are kicked out, these hydrogen bonds over here between the water and the hydrophobic groups is going to be broken, and that's going to release energy as heat. And as we know, the release of heat means that delta H is negative. However, one thing to keep in mind is that when these hydrophobic groups come together, you need to create new bonds at this interface, which means that delta H is actually going to be positive, and that value is way higher than the negative delta H whenever these waters are being expelled. So overall, as a summary, delta H is positive and delta S is positive whenever these two hydrophobic groups are coming together. And then that creates one of the four scenarios that we discussed earlier. So if delta H is positive and delta S is positive, Well, that's only going to be spontaneous whenever we're at high temperatures, right? Because we want to overcome this positive delta H value. Well, it turns out that the delta S value in this scenario is actually going to be way higher than the delta H. So your temperature doesn't even have to be that high in order to counteract the positive delta H value. So we can say that this reaction is spontaneous at most temperatures. And not only is this scenario important whenever two hydrophobic groups are coming together, but this is important in terms of just general protein folding. Whenever two portions of a protein are coming together, you're pretty much going to see an exact similar scenario wherever water molecules are going to be expelled. So the second Gibbs equation is going to deal with Le Chatelier's principle, which, if you remember from general chemistry, it describes whenever you have high concentrations of either your reactants or products, the equation is going to go towards the side wherever you have the less concentration of. Okay, so we'll discuss it a little bit more later on. So you can think of this delta G as your actual Gibbs, this over here as your theoretical Gibbs. And that's your theoretical because it's set at a pH of 7 and it's under standard conditions, which means it's under 1 atmosphere of pressure. And more importantly, it's at 25 degrees Celsius and at 1 molar concentrations. And I highlighted these last two because these two factors are things that we can manipulate this equation over here, so that if, for example, the theoretical Gibbs is positive, we can make it so that this whole equation is going to be negative, and vice versa. So the KQ can also be rewritten as products over reactants. So let's say we had higher concentrations of our reactants compared to our products. So Le Chatelier's principle is going to favor the side with the lower concentrations. So this equation over here properly reflects that. So think about it. If we had a higher concentration of reactants, that means we have a higher denominator than our numerator, right? So that means whatever value is inside of our natural log is going to be less than 1. And then the way the natural log value works is if it's a fraction less than 1, it's going to give you a negative value. So that means that there's a higher probability that this equation is going to give you a negative value. And then vice versa whenever you have the opposing concentration. So if you had a higher concentrations of products and lower concentrations of your reactants, your reaction will not want to go through, which means your numerator is a higher value than your denominator. The value inside of your natural log is higher than 1. And so your value is going to be positive. So a real-life example of this delta G equation is in the matter of glycolysis. So glucose being broken down into pyruvate. So as you can see, in the intermediate of F6P, you can either produce two products, G3P, which goes on and eventually produces pyruvate, which is what we need, or DHAP, which is kind of a dead end. So we want to maximize G3P production, but the downside is that this reaction is not favorable theoretically. So let's say we are given a certain concentration of our DHAP, our reactant, and a concentration of our product, our G3P, at a certain temperature, and we are asked to determine the free energy value and determine whether the reaction is spontaneous or not. So first things first, we're going to set up our equation, put in the products in the numerator, the concentration of the reactants in the denominator, plug in our theoretical delta G value, and then determine our R value and make sure your units are matched up. So the most common value for R is 8.314 joules per mole Kelvin, but as you can see, the theoretical Gibbs is in kilojoules, so we got to make sure to divide our R value by 1,000 to get kilojoules, and then make sure to convert the Celsius temperature value into kelvins, and then after that plug in our product and reactant concentrations. When we do this, this is the value that I get over here. And then when we add that to the theoretical Gibbs value, our final answer is going to be negative 3.30 kilojoules per mole. So this is going to be a spontaneous reaction. So what is the significance of this? So as you can see, if we're under standard state conditions, right, that tells us that this reaction is not spontaneous because we're given a positive theoretical Gibbs value. But if we manipulate the equation so that we find a way in which DHAP is a higher concentration of G3P, and also the fact that our internal body is set at a high temperature of 37 degrees Celsius, we are able to overcome the fact that this equation under standard state would not be able to go through. So the final delta G value to discuss deals with the concept of redox. So the N value finds the moles of electrons. The F is a constant, which can be displayed in either two of these units. And then the E value is the reduction potential in the units of volts. So this E value is something that you'll typically be given for in a problem. A common application of this delta G equation is the electron transport chain, where an electron is essentially dumped off onto complex 1. It's transferred around these 4 complexes, and then this allows the ATP synthase to produce ATP. So the first step of this process involves NADH, right, which carries the electrons, to send them off to complex 1. Complex 1 is also known as FMN, which is flavomononucleotide. And as long as FMN has a higher reduction potential than this NADH, it's going to accept these electrons. So from the images, you can tell which one is getting oxidized and reduced based on the hydrogens. So if something is losing hydrogens, it's getting oxidized. If something is gaining hydrogens, it's getting reduced. So each hydrogen you can think of carries its own electrons. So here it's H2, which means it's carrying 2 electrons. From there, those 2 electrons bounce towards the subsequent complexes, and then you're able to produce ATP by the end. So if you're wondering what the delta G value is for this first step of the electron transport chain, you're going to have to use that delta G equation. So first things first is to grab these 2 equations. Either it's given to you or you'll fetch them from a chart. You're going to identify the higher and lower E values. The higher value, you're going to keep it as is. You don't touch it. But as for the lower value, what we're going to do is flip the arrow, and we're also going to change the sign on the E value. So now instead of negative 0.32, it's positive 0.32. After this, you're going to add these E values together. And depending on whether your teacher asks you to determine the net ionic equation or not, if your teacher asks you for it, you're going to make sure to cancel out both sides of the arrow in which are identical to one another. So the N value is going to be your moles of electrons. So it was 2, as you can see over here. So we dealt with 2 electrons. Your F is a constant, and then our E value we determined was 0.101. Make sure the units cancel out, and our final answer is going to be a negative value, which tells us that it's spontaneous. Final point I want to mention about this equation is that our E value, right, our reduction potential, is an intensive property, which means that if your electrons from one equation isn't enough to cancel out both sides of a reaction, and you have to multiply it by a certain value, you do not multiply that value to the voltage. So let's see what I mean by that. So if, for example, we're dealing with these two reactions, and we're given these values over here, the first step is to identify the higher and lower values. Higher we keep as is from before, and then we are going to flip the sign on the lower E value. But as you can see, the electrons do not cancel out. What you're going to have to do is multiply one of these equations, or both, so that these electrons cancel out. So if you multiply this whole equation by a factor of 2, you do not need to multiply this E value by that number. You keep it as is. So once you do this, you're going to do exactly like how we did last time. You're going to add these values together, get your net E value. You cancel out your electrons, and then you get your net ionic equation. And then from there, you plug in the values. So we dealt with 2 moles, right? So we adjusted the 1 electron to 2 electrons, and these 2 electrons cancel out. So our N value is 2. Our Faraday's constant is 96.5, and then our E value is what we determined from earlier. So cancel out the units, and we get our answer. That's it for today's video. Thank you guys for watching. If you like the video, please leave a like and subscribe. And if you need any study help, I provide online tutoring services. See the link below for my tutoring website where you can schedule a session. Have a good day, guys.